Sir, Shekhar sir, can you
Yeah.
able to share your slides, sir?
Okay, now itself or
We can able to check it, sir, whether it have been
check you
working.
want to check. Okay.
Shekhar sir, can you able to share your slides, sir?
Are you able to see?
Itself, or we can able to check it, sir, whether it have been working.
Hello, are you able to see now?
Yes, sir, I can able to see you, sir.
Okay,
I can able
no,
to see.
screen.
Yes, sir, perfectly.
Okay. I'll come back again. I'll close and come back again.
Yes, sir.
Thank you.
Sir, good evening, sir. Can you able to start, sir?
Yeah, you can start. It's time.
Thank you, sir.
Okay, you are just starting some welcome address or something?
Yes, a short intro, sir. Short intro about.
Okay, please do it.
Okay, sir. Hello, young leaders. Welcome to today's 36th webinar session. Dr. Shekhar, sir, our professor of eminence and our beloved former dean will be giving us a short presentation on basic of measurement. He is the person behind successful completion of Perambur flyover, despite IIT has failed to design the project. I personally admire the below quote of Shekhar sir, always in my difficult times of life. See, life may let us down so many times. It only up to you whether you want to strike it back or not. Keep trying. Yes, sir. Whenever life has been striking me, we have been looking you. More than 4 decades you have been in our college. You have been serving our students. It's a pleasure to have you, sir. In spite of your busy schedule, you have been here to share your knowledge. Thank you, sir.
Thank you, Satya. So
Thank
you can
you,
start.
sir. Yes, sir. Sure, sir.
Satya, thank you, and welcome to all of you who are joined here. It's a nice evening, and really I'm very happy to be back here giving a lecture because I've been missing this for a long time. As you all know, teaching is my passion, and then this is a very nice chance. There are two submissions I have to make, especially for this, because the experimental techniques is a very favorite subject for me in my ME structural engineering. I've been teaching it for a very long time, number one. Number two, my PhD work and all my guidance were on experiments. So I've been down to earth, an experimental person, day in day out dealing with the instruments, their adjustments, calibrations, all such stuff. So when Satya that is some basic of measurements, I was really very happy because a thing which is known to me as in with, but as you call it, is basic of measurements only. So you will find I'll just design my talk like some popular video or something. Then main basic points that we should have before going to any measurement, because you may use a very big highly sophisticated instrument, but unless you have got basic knowledge of what are the other things behind it to use it, it is not going to be useful at all. It's like, you may have a great what do you call a silencer gun with you, very latest silencer gun, but with the silencer gun if you go make noise and then try to shoot, it's not going to be useful. So it's just joke apart. So that's what I say, there are a lot of things which you should know whenever you plunge into any particular activity. So that way we are going to have this. And in the process, I'll also share some of the experiences which we have. The time is not going to be that much available, but still I think that we should be able to do some justice for the work that has been given to me. So I'll be just sharing the screen with you with a question to you. That when was the first measurement made on you? That's the question idea. And also the video clips that I'm going to present one after the other, you have to guess what is it being measured in that particular thing. So my first question is, what is the measurement made on you? Just watch this clip. One second. You would have guessed it by now. So as you were born, measurement is made on you. So the first measurement, maybe that is what? Finding your weight, telling, sharing that weight with all the people around the place. Look at the second one. It's going off.
Sir, excuse me, sir. We can't able to see the video, sir.
There's some problem with the video. what I'm trying to show is I'm trying to show number of the measurements made on you, made on us, everybody. We consume a lot of energy, and how do we measure the energy? That's my next video, which most of you would have. Sorry, there's a problem with the video. Trial, it was good. Maybe I'll just flash it and then show it and stop it so that you'll be able to guess what's happening. .05 meter, it's a record, world record. Another hero is coming here. As many of you know, the swimming champion.
Sir.
Yeah.
We can't be able to see the video, sir, video streaming.
That's flashing, right?
No, sir.
Nothing is there.
No, sir. We can able to see only the slides, sir. Slides only we can able to see.
It's not playing.
No, sir. We can't able to see it.
Okay, I'll skip this. So what I am trying to establish is that we keep on measuring right from the birth, on our body and around us, everywhere. So we use lot of gadgets, and then we try to take some steps, precautions in getting the correct values, everything. So in these measurements, what is that we should know basically is what is our question now. And let me go to the various devices that we use, starting from a simple tape, a Vernier caliper, micrometer. This is now I'm very much in demand, as you all know. The oximeter, and what you read there is going to decide whether you are going to be put into the hospital or you are safe at home. A proving ring, which I have used a lot of times and a lot of places in my laboratory. A pressure gauge, a very beautiful concept with which this pressure gauge has been designed. Very simple. Many of them, like it's very ingenious, basic concepts, ideas that has gone into making such gadgets. A orifice plate to measure the flow. A venturimeter, another to measure the flow. And vibration analysis was my favorite area, in which what you see here is a vibration analyzer with a wireless accelerometer by the side of it. So this gives you the complete data about the vibration of any object that's happening. And for our quick measurements, these are called accelerometers, as many of you might have known already. And the vibration meter is in a handheld equipment, which is quite handy, wherein you can just find the various vibration characteristics of any vibrating medium. So we have come a long way in making a lot of objects and using them for the benefit of the society and the mankind. And basically the things are remaining the same as what one should know. So what's the measurement? As you see, quantitative comparison between a predefined standard and an unknown magnitude is what we have to define as a measurement. And what do you require for a measurement? You require a predetermined standard. You see, you saw a tape and you saw a scale, linear scale. That is the standard which you believe that what it shows is an inch or what it shows is a centimeter. Then using that, you are trying to measure. And it is an internationally accepted one, and then try to use it. And then you are using an apparatus used or the experimentation adopted must be provable. That is the one thing, because you say you use an apparatus, then that apparatus must be accepted by everyone that it is meant for that purpose. The two physical aspects of the measurement are should have a physical device to carry out the measurement, authentic, approved, reliable, and acceptable. And a standard predefined quantity, you call it as unit, which is unique in depending on the varied nature of quantity like length, mass, time, temperature, flow, etc. So we must have some quantity that goes to define or measure these quantities. So the instruments, that the device, physical device, can be divided into a number of types or classified into a mechanical, which uses only mechanical means, an optical, which uses light, electrical, which uses electrical concepts, electronic, which uses the electronic principles, and a hydraulic, which uses pneumatic or pressure things. And these are applied to either a digital one, which shows the display as a digital or analog device, or there could be one which, like our watches, you have got both analog and then digital combined together, you call it as hybrid. Then there is a null type which shows the reading just like that, or moving parts are there, it's called deflection type. If it is an open one, that is, it shows the reading, that's all. If it is not going to go around and control itself, then you call it open loop. And if it goes and control itself, you call it as a closed loop. This is the physical device. Then I told you that one more thing required is a unit. The unit, as you all know, you've got basic units of mass, kg in length in meters, and time in seconds. And you also should know what is this basic units and how they are defined, which also is predetermined. That's why we say it's a predefined quantity. It's a predefined quantity, and you have to define only in a particular manner. In this way, I'd like to share with you an information some of you may not know, that in 2019, some of the definitions for these basic units got changed. And I don't know how many of you know that. Because I was teaching my class this time, I could see and everything I could say. So kilogram kg, we normally think and say the mass of a specific platinum iridium alloy cylinder kept at the International Bureau of Weights and Measures at France. But sorry, it has been changed now. In 2019, it is redefined by taking the fixed numerical value of the Planck constant, h to be this. So accordingly, it is combined with the meter and second to be defined. And meter, not much of change, though there is some ornamental difference is there, but we can still go by distance traveled by light in vacuum during a time of this particular second. And the second is defined as so many times the period of vibration of a cesium atom. So it is actually the frequency of this atom and is vibrating. How do you measure is what is given. So as I told you, a physical device and the unit, they go to combined measurement. So basically we should know the various measuring units. What is the need to measure? Which of course everyone knows. You have to obtain the 2 dimensions of your part, or to convert physical parameters into meaningful numbers, or to test if the elements of a system function as per the design. You design and then see whether it is really functioning that way. To evaluate the performance of a system, whether you got a specific speed of an engine, whether the train runs in a particular speed or whatever it is. To ensure the interchangeability of these particular things, values, to establish validity of the design, to ensure the parts conform to the established standard. There are some defective parts. How do you say defective? Only if they don't satisfy your testing standards. What is the testing standards? You require a specified thing, you have some tolerance, then you want to satisfy that. That is how you detect the defective parts. And you want to establish a scientific concept, to estimate a natural phenomenon, or to supply data for a detailed analysis. For all these, you require measurements. Methods of measurements, I can say as a direct measurement, that is, you directly keep your device and then take the weight, take the observation. For example, in the physical balance, you just balance the 2 arms of the balance and then try to find the weight. So you don't have anything to calculate. You simply take it and from there. Whereas similarly in the scale or tape, you are able to directly get the reading. But the indirect measurement is the required value will be obtained after calculations made on the observed parameters. That means you may calculate length, depth, and breadth, and multiplying with density, you may get the volume. But direct measurement is you get it directly. And how do you, the process of measurement also, the 2 types. Direct is, as I told you, the physical balance, scale, tape, and all that. There is no any conversion process is coming in. There you call it as a direct measurement. But when you convert it to something else, one energy is converted to something, some other energy, then you call it as a process of transduction, transducing, strictly speaking. So process of converting one physical variable or effect to another in the way you try to measure. That is, example, you convert a displacement to a voltage. There is a LVDT, linear voltage differential transducer is there. From then in the LVDT, a displacement of a spindle is converted into voltage change, and this voltage is measured. Similarly, force into a displacement in a load cell, it will be compressed, and then that compression will be measured, like a spring, wherein you compress the spring and you know the stiffness of the spring, then you try to measure the load. These are called the transduction. Now I'll just give the various list of transductions that are being done in order to measure the measure. Similarly, force into a displacement. So displacement to displacement. You are contacting spindle. So one spindle is contacting two places, one place moves, other place also you measure. Or a light pointer is simply moving, a distance is moved by the light pointer, you just measure the movement of the light signal that is there. It's a direct, it is called displacement to displacement. As I just told you, displacement to change in electrical quantity, it could be either resistance can be changed as in the resistance strain gauges, or capacitance or inductance as electrical quantities, they can be changed. These are measured and then your displacement is obtained. Or vibration to voltage. This is a very beautiful concept. Like a piezoelectric material is actually, when it is vibrated, it is emitting electricity, and then you are able to measure the voltage. So accordingly, only our accelerometers are designed. Force to displacement, as I told you, the springs and proving rings. We saw one proving ring in the earlier slide. So there a circular disc is being compressed, and because of this compression, a definite compression takes place, and it is only because of a particular load. If you are able to measure this compression and connect it to the load, then you are able to get the proving ring. This is what is converting force to displacement. Similarly, pressure to displacement. A pressure gauge, which you have seen earlier, a pressure is actually pumped into a small thin tube, and because of the pressure, the tube bends and then it changes the pointer in the dial. That is the concept of a pressure gauge. So similarly, bellows or diaphragms are also used to convert pressure to displacement and measure that. Flow to pressure, the orifice plate, you saw a venturi or nozzle. Here and all, a flow is converted into a pressure, and you measure that pressure and then try to measure the flow. Or flow to a displacement by rotation. Piston type flow meters or turbine flow meters are the examples for doing this. Temperature to displacement. Differential expansion sensors, bimetallic probes, they are all converting the temperature change into a displacement of two different objects or two different pieces. From there, you make the measurement. Temperature to electric current, these are called thermocouples. Temperature to pressure, they are called pressure thermometers. Temperature to electrical energy, what we use now commonly due to the corona effect is that, you know, everyone uses this AR thermometers everywhere. And here what happens is the temperature is converted into electrical energy, and in turn it is shown in the infrared thermometers. So these are all the transduction operations which are used to convert one energy or one form to other form and try to make the measurements. Now, when you make measurements, there are a number of characteristics that one has to be concerned with, and then trying to make it happen or make it available in the instrument that you have. This is very, very important for making a reliable measurement out of your instrument. So these are various characteristics I'm going to just show. First is the linearity. What you measure and what you apply input and output, as normally call, should be linear, because as you see, a straight line has got a lot of advantages to detect a value from one value to from the other. Whereas on the nonlinear case, it's going to be chaotic and cumbersome. Normally, it may not be possible. So you see, just if the performance is linear, our measurement is going to be very good. So we just expect the characteristic of a linear characteristic from our instrument or from our gadget. Now the same linear straight line that you get out of the input and the output connection, it has got a slope. So this slope is called sensitivity, and this gets affected by number of factors. As you see here, the temperature affects the sensitivity of the platinum resistance thermometer here. As you see, the three different lines with three different slopes, which means three different sensitivities. Repeatability, this is one very, very important factor. Today I measure something, use the same instrument, measure tomorrow on someone else, and again the day after tomorrow you do it for someone else. Every time, you know, there must be a reliable output I should be able to get. So this is what is repeatability is called. So when you see it in the graph, it's just, you can see they are all just following a particular path and then goes. So the repeatability should be available in your measurements wherever, whenever you are going to take the measurements. Then the hysteresis, as you change your, like positive to negative measurements, and the variation must be, strictly speaking, you want a straight line from left to right, which is not going to happen at all anywhere in any instrument. So what is the variation that which it is? That is your starting value itself. It may take a particular time. When you give an input, immediately you may not get an output. It may take certain time or certain value to get the output. When it dies down also, it may not immediately die down. So this is what is shown by what is called the hysteresis characteristic of a measurement. So this is also very important to note, and then keep it as minimal as possible. Next is accuracy. Now this accuracy and precision is very, very important, because everyone wants an accurate measurement. You just want to see the temperature. Supposing it shows 105 for you, naturally you are gone, you are out. So the equipment, the instrument should give a very accurate value. So what you just defined, accuracy is the closeness or nearness of the reading of an instrument to the real, correct, true or theoretical value of that quantity. You want to measure the temperature of the body, then if you want to get 98.6 degree Fahrenheit, you must get 98.6 Fahrenheit for a normal person. Then that is what is reliable. So then you must rely on this thing. So accuracy is very important. So if it is not accurate, naturally, if it deviates from the theoretical value or the real value, you get an inaccuracy coming into picture. And this inaccuracy is what you call it as error. So error in the reading obviously is a measured value minus actual value. Can also be expressed as a percentage by dividing by the measured value, actual value into 100. Accuracy depends not only on the device imperfections, but also on temperature, humidity, wear and tear, and vibration. So it is the environmental effect also is in. Later we are going to see what are the various factors which can affect our accuracy or precision, etc. So there we will see how these are going to affect our performance. Then precision. Now the precision, normally we have a feeling that exact value is a precise value, do and all that. But in this our metrology or our measurement subject, we say precision is the repeatability. If the value can be, you are able to do repeatedly again things, reproduce the same reading again and again, then that's what is called as precision. So if 2 values are taken or 5 values are taken, what is the limit with which it varies? That is what is trying to give it as a precision. Now, unlike our accuracy, which is being affected by the environmental conditions, precision depends only on the device imperfections. So if the device is perfect, then precision also will be good. Repeatability is available. So next slide will show you this difference. So here you can just see bang on target, exactly in the bullseye. If you're able to hit, then you call it as a good accuracy, and also good precision also, because you see all the 3 dots are going and then hitting in the bullseye. Same, bullseye is accuracy, same place is precision. They can take it that way. So look at the next one. There you call precision, because all the 3 dots are able to go and hit the same point, but not at the bullseye. So accuracy is lost, but precision is there. The third case is a bad case, wherein no accuracy or no precision. So this will help you to understand the difference between accuracy and precision. Then comes the readability. The readability, naturally, that is quite easy to understand. If you have a display which is very flashy or not very clear, very dull, naturally what you are going to read out of it is not going to be reliable. So this is ease with which the readings of a measuring instrument can be taken, read. That is what is called as the readability. The ability of the instrument to have its indications shown in a meaningful manner. Normally what happens is, whenever you are able to make the graduations in the device very bright and then very dark, and also you just give wide space graduations, it may be easy for you to do that, to read that. This is what is we call it as readability of a measurement. Now, this is one most of us have done in our laboratory, the least count or resolution of an instrument. It is the smallest or least value that you are able to measure using the instrument, readout scale. So as small value you want to measure, that is what is going to make this instrument going to be very, usable or not. So there's a minimum value of the quantity that can be obtained from the instrument. You define it as a least count or resolution. And based on our requirement in our experiment or our application, you have to choose a proper instrument. Choosing a very big range of instrument or where a smaller value is going to be not going to be helpful for you. So it is not going to be possible to. I'll take the questions at the end. So least count, many of you know the vernier scale, the number of vernier readings, number of vernier divisions, total number of matching with how many main scale divisions that were MST, VST you might have heard. So you just find out the least count, and then using this least count, you are going to measure the reading. And in the micrometer, it is going to be the pitch of the micrometer divided by total number of circular scale divisions that are available. The next one is to be seen is the span or the range. Now the span or the range refers to the maximum value that can be read out of the instrument. So sometimes you require to measure 10 millimeter deflection. There you cannot use a 2 mm dial gauge and then try to measure a 10 mm deflection. So what you want to do is you will go for a 50 mm dial gauge, which means you should choose a dial gauge which has got a higher span or higher range. That's what we call it as a range or the span of the instrument. Now, obviously, when you go for a very high range, you may not get a very smallest value, will be only slightly more than what normally is available in a smaller range. So the range has got a direct bearing with the least count. So more the range, then naturally the least count also will be higher value only you will be having. So I'll just show 2 slides to explain this. So you got a number of dial gauges here. As you clearly see, this has got the least range because the spindle can move only this much. So moving on like that, you come to the bigger dial gauge. So this bigger dial gauge has got a larger spindle, so which means the range of this is much more and the largest than this smallest one. Similarly, in pressure gauges, they may measure either 500 kg per centimeter square or 100 kg per centimeter square, 20 kg per centimeter square. Depending upon the application, you choose and use a particular range of the instrument. The other point, of course, when you know all the characteristics and of course the various for the various instruments, the important factor that you have to keep in mind is the inaccuracy that can be creeping in. You just say that you got a very good instrument available and you are also an expert to use that. Still, I can say, compare these 3 different scenarios. That is, you use 3 different instruments for measuring a particular quantity. When I say 3 different instruments, you may use a vernier caliper, or you may use a screw gauge, or you may use a scale itself for measuring distance. Now, when you measure and then try to see, these 3 values will not match. Or you take 3 vernier calipers, and then try to measure the same quantity. So there again, you will not get the same quantity for the 3 readings that you are trying to get. Or the third scenario is use only 1 vernier caliper, but on the same place, you try to take 3 readings. Mostly you may be getting the correct value, near value, but in many of the times they may not match. This is where we just say there is going to be some inaccuracy, some deviation from the correct or true value that you are having. So in all the above 3 cases, no one can guarantee to tell the 9 readings are the same and correct. It can never be. So the difference between the 9 values and the true value is called the inaccuracy, which we term it as error in the measurement. The aim should be to make the uncertainty or the inaccuracy as small as possible needed for making the conclusion in the experiment, because it always depends upon what we try to find. Because for some observations or some experimentations, no, you may require only a higher range, and then inaccuracy or error may be allowable for a particular level. For otherwise, there could be some other situation wherein you reach a very measurement wherein the error has to be very, very small. So it all depends upon what is the requirement of your experimentation. Now we divide the errors into mainly two categories. One is called the accidental errors. These accidental errors are random in their occurrence and variable in magnitude. So I cannot say this error is higher now. Next instance, it may become more, and the value also may vary from one value to other. This is what is called as an accidental error. This follows the statistical law. And if by the statistic rule, you may be able to converge on a correct value. The main solution for solving this is take as large number of readings as possible and try to apply statistics. So obviously, as you all know, when you have a large number of readings available and then try to take the standard deviation, that is going to be the measure. So if the standard deviation is very less, naturally you can say your observations are reliable. So as you take larger and larger values and take the statistical means, you will be able to arrive at the correct value. These are called accidental errors. As against a systematic error. Now here, this is the problem. This systematic error will not follow any magnitude or direction. It will not have any definite magnitude or direction. And by repeating large number of times the same experiment or same observation, same reading, you may be deviating from the correct value to a bigger distance also. So this may cause more serious deviation from the correct value. So if the existence of this nature of systematic error is established within certain limits, because this depends upon mainly the instrument itself, the instrument inefficiency or deficiency. So if I can point out that, you can calculate and correct it every time you take the reading. So the existence or nature of the systematic error is established and is within certain limits. Corrections can be applied at every time the reading is being taken. And how do you get errors? Because you designed, you got an instrument and then you're using it. How do you say the errors are coming? So errors, the source of error are, obviously the first one is the aging, wear and tear. This is systematic error. This occurs either the reading will keep on reducing from the correct reading, or reading will keep on increasing from the correct reading. So this is systematic error arising out of the frequent use of the instrument. We call it as going out of calibration. Then this requires a very important aspect of any instrument called calibration. Calibration is the process to say whether your instrument is showing the correct readings or not for the observations that are made. So for knowing that, what you do is you take a standard instrument, and with the standard instrument, compare your instrument and then try to see where the discrepancy is there, how much discrepancy is there, in what direction is there, how the correction is to be applied. So calibration is a process of comparison of the observed readings from the instrument with that of a primary standard meant for that instrument. So the proving which I shown you in the earlier slide is actually very useful in calibrating the machines, compression machines or tension machines, depending upon the type of proving ring. So the proving ring will be kept in the machine. The proving ring is supposed to be from the National Physical Laboratory certified. So you know whatever the reading that says are the correct ones or authentic ones. So you put it in the machine and apply the load onto the proving ring and compare the load given by the proving ring, detected from the proving ring, and the reduced from the proving ring and the machine reading, machine load, then compare. So like that you can do and then make a calibration chart and keep it with you so that you can get things. So this is very, very important. So you do this calibration, and periodically we are being insisted to do the calibration for any machine. If a machine is not calibrated, then it is not reliable. It's like our getting accreditation for many of our courses we run in engineering colleges. So you should get accreditation now and then, because only then it is being certified to be worthy of its value. The instruments or machines are also the same thing, and you have to do the calibration periodically. Instrument reproducibility. Conditions different from that existed during the calibration process will lead to variation in readings. For example, you calibrate at 20 degrees centigrade and get the readings, but when you're using it's going to be 40 degrees Celsius. So obviously the readings will be way off. So either temperature, friction, backlash in the micrometer screw may lead to this type of errors called instrument reproducibility. So these are systematic errors which can be corrected. Many times it will be corrected, but sometimes accidental also can take place. This is called the instrument reproducibility error. Another error, source of error, is the measuring arrangement. That is, you fix the instrument in axis with whatever direction you want to get the displacement. That's most important. And if you just try to slightly put your spindle inclined and try to measure, what you are measuring is not going to be the correct value or the expected value that you are going to get. Similarly, instrument supporting system, that should be perfect. This many of the times we land up in our experimental procedure, either in site or in the laboratory, that we don't mount the system properly. The system, that is the instrument supporting system itself, will give way, and then the readings will be way off the mark. So this is a common problem that's happening many times, and especially in the optomechanical error, instruments, wherein the displacement is shown by a light ray which is going to come out of an optical instrument, then obviously if there is going to be some inclination in the fixture of this instrument, then your optical ray that's coming out will go away from the correct path, and then what reading you are going to get is not going to be correct one. So that is why the measuring arrangement is one of the very important source of error, wherein you must be careful in avoiding them. Then comes the nature of workpiece. This, very well, especially those people who have done their hardness testing and all that, they know you have to prepare the surface of the object before using it. Even similarly in SEM machine also, you would have known the SEM machines, whatever piece that you keep, there's a lot of preparations are needed earlier on the workpiece. So this will try to change the nature of the reading that you get also. So that is why this aspect is to be considered carefully, so as to prepare the workpiece properly before the observations. The hardness, roughness of the workpiece, etc., and the relative pressure exerted from certain instruments influence the reading. So especially for hardness test, you all know, you try to apply a force onto the surface of the object and try to get the value. So this will affect that. So that is why nature of the workpiece has to be ascertained first to avoid any error. Then comes, as we have seen in the reproducibility itself, the environmental conditions. As already seen in the reproducibility, humidity, temperature, pressure, electrical or mechanical field will influence the readings if they are different from those existed during calibration. Suitable corrections can be applied if stipulated by the calibration chart. So calibration chart gives you a standard temperature in which it was taken, and you know the field temperature. Naturally, you can apply the correction and do that. So this is possible because this is a systematic error which you can remove. Interestingly, the magnetic aspect also affects the performance of any laboratory readings, etc. Recently, we had in Kalpakkam Atomic Power Plant, they have a problem of like very sensitive machine to be installed, but the reinforced concrete building, because of the steel present there, it gave a lot of problem. So then they had to go in for different reinforcement. So we had to do some project on using the stainless steel, which is magnetically insensitive. That's AS316 or so. So with that, we had to do a lot of tests and then try to give them that design using the, so then they set up the one laboratory itself fully built using the stainless steel. So that's why we see the environmental conditions, they play a very big part in creating this human intervention. So observer skill. This is the human element in the measurement process, which plays a decisive role in spite of modern technology and improved automation. Because many times nowadays you directly feed in the value to the computer and then try to get the result. As many of the testing machines now, They don't fix an external dial gauge. They don't try to measure the reading on the dial load indicator and then try to corroborate. The response and the load is directly fed into the computer, and then the computer plots the stress strain diagram or the yield starting point or the ultimate load, everything. So that way you are able to minimize the human intervention, but it is not going to happen in all cases, especially in field measurements, etc. Our human intervention is going to mean human interaction is going to be more available. So in such a case, measurement of physical quantity will vary from one another. So that's why normally we insist, if somebody takes reading in a particular place, we insist that same person takes the reading until the experiment is over. Because if you just change, naturally the other observer who comes and then tries to take the reading, he has his own way of taking the reading, and one reading will change from the other. So even for the same observer, depending on his or her physical or mental states, measured values may vary. So this can be avoided. These are going to be either systematic or accidental. So obviously the best way to avoid these errors are having a well-trained observer or the one who takes the reading with a lot of practice, so that for utilizing or using that particular instrument, naturally he is well versed with using that instrument, and these errors can be avoided. So these are the various sources of error. We try to do that. And how do you avoid these discrepancies? As we had seen the various types of errors and also causes for it. Obviously, the way to avoid them is looking at the nature of various errors. The following are the steps needed to reduce discrepancy. One, obviously, is a periodic calibration. An electronic instrument or a mechanical instrument, whatever instruments, naturally a periodic calibration, like the regular servicing of any machine is required. This periodic calibration is very much needed. After calibration, naturally you have to apply the necessary corrections in the readings that are taken if needed. Proper handling of the instruments is very important, and training and skill of the observer. And lastly, the statistical analysis. The statistical analysis, the basic knowledge of the statistics has to be known, because when you take large number of readings, you'll be trying to take what is called as a mean, mode, median, and the standard deviation. With all this, you try to plot and see and get a curve from which you should be able to reduce the reading. This will be required when large number. For example, when we test our concrete cubes in a very big project, we get hundreds of cubes being tested, and naturally we try to plot a statistical plot, and then from there we try to arrive at the strength of the concrete. This is how we normally do. And so as we have seen so far, the characteristics of the various instruments, then what are the various possible types of errors, and what are the sources of these errors, and how to avoid all these errors are the basic principles one should know whenever we try to use any instrument. The instrument could be anything like, like ordinary mechanical instrument, like your simple dial gauges, or it could be simple calipers, or it could be electrical strain gauges, or it can be vibration meters, or some vibration oscilloscopes. All those things we can be using. But for all these instruments, basic things are the same. That is, what you understand, what you do, basically are going to be the same. This is what we call it as the basic of measurements, which everyone should be aware of whenever we are using the instruments. And of course, before closing, I have to share with very important information about how our first engineering college came into the country itself. I'm happy to say it is only because of the measurement. The measurement requirement only made the engineering college has to come into this particular country, because the British people wanted to know how much of land they owned. Because in England, if they start by their horse, within 3 to 4 hours, they used to reach one end of the country to the other end of the country. But in India, when they try to move, it takes days and days. So they were wondering how much of space that they really own. So then they wanted to make the extent of the land that they owned and then they were ruling. So for that, they really wanted to measure, do a survey. So for that, they started what is called as a survey school. And the survey school is what is ultimately blossomed into a big engineering college, College of Engineering Guindy, and then a very popular Anna University now. So that is what I would like to share, that measurements are the part and parcel of our life, and especially as a mechanical or civil engineer or whoever engineering technologist that are going to be there, the measurements are very important, and we day in day out we are measuring things, and naturally when we measure things we should get at the correct values, and these correct values you should ensure and then know how to get them. And this is what is ultimately I would like to say to all of you, that keep measuring but correctly. Thank you.
Thank you, sir. Thank you, sir. Sir, my name is Damodaran, sir. I'm going to give a feedback for this section, sir.
Okay.
First of all, thank you for teaching us the basics of measurements. It's like recollecting all the things we have learned. But one thing I have particularly, I want to say that province circle that I did not know that before, that I learned it today, and the service school, the trivia about the history of our engineering colleges, that was new to me, and all the sources of errors, and then the different type of gauges, etc. And we have learned it today there, sir. And it will be very useful for us. I think it will be very useful. Definitely, it will be very useful for us for recollecting, and whether people will ask the questions about these measurements, they will definitely come from the basics. As you already told that when you know the basics, we can learn anything in measurements. Thank you, sir. Thank you so much.
Thank you. Any questions are there? Somebody sent some questions? Because somebody raised their hand in between. Hello. I look at the chat. He is there in the chat. Satya, are you there? Hello.
Hello, sir. Good evening, sir. I've been there, sir.
Hello.
Hello, sir. Can you able to hear me, sir?
Yeah. I can hear you, but someone raised their hand. Is there some questions available, or somebody wants to ask questions or something?
Sir, I have one small question, sir.
Yeah, please.
Nowadays, based on the lot of digitalization, many students has been doing the measurement in the form of digital forms.
That's right.
Whether it's going to play a very big difference without touching this kind of basic instruments, because many of the students of the past 3 or 4 years, I can able to say
Yes.
what they have been telling is, sir, we have been using a most digital thermometer or digital vernier gauge. I just want to know what is the impact of it, sir.
Okay. See, even now in our laboratory itself, dramatic changes come, because earlier days, if I want to test a beam specimen, I used to take 1.5 days to complete failure of the specimen from one start. But now that and then even taking the deflection readings or the strain readings are become so handy that surprisingly, in one of the very big experiment recently, just they finished in 1.5 hours the complete breaking of the specimen. And the reason is obviously, as you said, we have got some digital things are available. But basically, as you see, even there is going to be a lot of things which earlier you must things also. For example, as I told you, the handheld infrared thermometers also, Now, if you don't hold it properly in a proper angle and then sense, because as you see, most of them are simply using it, but in every or not. In where I told you the complete thing is digitized and then taken to the system and then drawn. It may so happen that when the automatically wages onto the thing, then one to be careful in doing that. So digital or manual thing, the care has to be always there, and there must be a sense of checking that must be available in you, because that comes by experience. And then try to see the readings are obtained earlier. And of course, its modernization helped us making our life comfortable. But still, I'll say a word of caution that please be alert in establishing that you are getting the correct readings.
Sir, thank you, sir. Thank you lots.
Okay.
Last final question, sir.
Yeah.
Sir, I've been very keen to ask these questions for a very long time.
Okay.
What made you to took that Perambur Bridge project, sir? Because a lot of failures has been there. Whether it's your basics.
Should I say it here or not? Because I was heading the structural engineering division.
Okay.
There is no other go.
Okay. So based on your basic songs from CEG.
No, that is there. No. This Perambur is a special case. Because of that, I have to say that particular answer, because given a choice, I may not have taken that. But basically, I have to tell, maybe I think it should help others also. As you join a job, you just don't do only what is required. You always try to do something more than what is required. And sometimes your boss or superior will make you do that, and then that is fine. Or proactively, you must take part in doing some extra things. Here in a teaching, which is normally called as mundane, you have to go to a class, teach and come back, correct the papers and give the result every day and out, do a thing. Internet have they took me to every single place they were going for their extension activities, namely the consultancy activities. So right from the day one I joined, I was going for testing, calibration, doing some calculations, transmission line towers, their failures, their analysis, everything which I've been doing. So over the years, the confidence has come to me because of this extra work that I've done. So that is very, very important. In every profession, if you can do some extra, that actually makes you much more confident in your profession. Naturally, I have to admit here, because of that, I had a lot of experience and confidence to take any design work. Earlier, actually, within 5-6 years I joined, we designed 16 and 26-story buildings in Sri Lanka. At that time, there were no multi-story buildings at all coming up here. As you see, 36-story building and all coming up in OMR. But that is not the case in the 80s. So at that time, your work was given by L&T for designing a 26-story building. Computers were very, mind you, there is not much of sophisticated computers available. You have to go to only IIM 370, run our SAP 4 software result, and then use that result, and then again go to the next day, run the computer program, keep on doing that. It was a tough job, but still we could do. So what I am saying is the confidence to do has come to me already. And that is why I've taken that particular work confidently, and then I completed the work. Though I know even IIT has failed in that work earlier, and there were some political problems also were there in that bridge. Even then, I could take and then complete it successfully. It is only because of the training and the confidence that I could get from the profession that I was involved in. I think I made myself clear.
Yes, sir. Thank you, sir. Thank you lots for your lot of knowledge sharing sessions. As your knowledge has been on a very strong part, we as a students has been getting beneficiary, and also all the Chennaites, all the Perambur persons has been getting the strongest bridge.
That is right. That is right.
Thank you, sir.
Thank you.
Thank you for the wonderful
Thank you
time.
very much.
Thank you.
Thank you very much. I can leave?
Yes, sir. Sure, sir. Thank you, sir.
After you. Okay.
Have a great evening, sir. Bye, sir.
Thank you.
இது ஆயிடுச்சுன்னு போனாங்க. கோவிந்தா லோகேஷ் பவித்ரா எல்லாம் இருக்காங்க. அம்மா